So today we are we will speak a little bit about again about analytic geometry, but there will be not so much analytic geometry. There will be more topology. Let's say differential geometry, or perhaps differential topology, but to deduce a theorem which is, let's say, purely algebraic, more or less purely algebraic. The theorem I want to speak today, or at least for the first part of today, is the Andreotti-Frankel proof of Lefschetz hyperplane theorem. And I will speak about one particular theorem of hyperplane section, which can be proved also by formal geometry, which will be the topic we will study after this. And but the proof by using formal geometry, I think it will be described by Bost next week. So the theorem I want to state this theorem, which is we take X be a smooth projective variety, D inside X, okay, I will simplify my life and will say that smooth ample divisor. And just to simplify even more, I will suppose that very ample. But this is not really a restriction. This is just because I'm lazy. And let's call this map I. So, and I will suppose that the dimension of X is at least 3. And the conclusion is that if I look to I lower star from P1 of D to P1 of X, this is an isomorphism. And the proof I will give, it's really concerning the, let's say, the true P1, the P1 which is given by loops. And the formal geometry approach will give the proof for the Grothendieck P1, which is given by the formal completion of this. This will come after. Just a remark. Dimension 3 is necessary. Example, you take X equal to P2 and D a smooth curve, smooth plane of degree at least 3, and then you say that P1 of X is trivial and P1 of D is big, is infinite. So, and this is due to the fact that the dimension. So it is no contradiction because of this hypothesis. And now I want to explain, and the proof will pass through a theory which I will very rapidly sketch, which is called Moore's theory. But let's say what we are going to do. We are going to, so just to give some definition, a cell of dimension of real dimension n is the x in Rn such that norm of x is less or equal than 1, and I then call it dn, and d is not a good letter, cn, and Sn is equal to 1. And if Y is a topological space, to attach a cell to Y means to glue a Y and Cn via Sn, like so if this is the space Y, what I do is this. And this is Cn. Now let's say that this is Y with a hole here, and then I can attach the and now what we will show. We will show that I will make a picture that here we have D, here we have X. We will show that we can find a small neighborhood of D, call it V, such that V is homotopically equivalent to D and inside V we will construct a space such that X is a space V X epsilon, such that X is equal to X epsilon with X is X is homotopically equivalent to X epsilon with cells of dimension at least n, the same n which wasn't noted here, which now is noted here, attached. So in some way, in order to construct X, you just attach, let's say, bools of dimension very big to this space which is here, this small space which is here. And now it happens that if X epsilon is a space and we attach to it a cell of dimension at least 3, sorry, let's write the thing like this, is a space and x1 is x epsilon with a cell of with a cell of dimension at least 3 attached, then P1 of x epsilon is equal to P1 of x1. This is a standard result in topology. In some way, cells which are dimension too big will not change the fundamental group because they are too big. So if you have a loop, you can always go around this. It's like this. What is Archer? What is this book in algebraic topology, which is you can find on the web? I think. Huh? Huh? Where is the T? Huh? H-A-T. H-A-T. C-H-E. If you write this something like topology on Google, you will find a book that you can download. It's very good. I mean,
excuse me, the theorem is in the complex setting?
Yes. Yeah. Everything is in the complex setting. So and now I forgot to give a name to the small neighborhood of D. I have to give back. I have to go back. Because this small neighborhood is, which I will call it the I don't know, W, and which is homotopically equivalent to D. And now I have P1 of D, which inside P1 of X epsilon, which is inside P1 of W.
Sorry, what is the difference between UW and U wrote P?
Sorry, yes, I forgot to, yes, so it's V. So this is an isomorphism, which means that this map is injective. And now you have, this goes to P1 of X. And yes, and you have this. So this is an isomorphism. So that means that these maps must be injective, which at the end of the day means that P1 of D in P1 of X is an isomorphism. So let's do it again. This is injective. Okay, I think no.
Because the composition is an isomorphism.
The composition is an isomorphism. So this means that this map is injective, because this is an isomorphism. And now this map must be surjective because this is an isomorphism. So that means that this map must be surjective. So this is an isomorphism. Okay? So the aim is to obtain V and X epsilon. So when I will describe Morse theory, I will in particular the first corollary of Morse theory is that a smooth projective variety is homotopically equivalent to a CW complex. Anyway, this can be taken for granted. And so that implies, so every smooth projective variety is homotopically how you write? Homotopically equivalent to a CW complex, which in particular implies that so I call it V exists. And V is open for the usual topology, for the Euclidean topology, open in X for the usual topology. By the way, a good reference for this proof is Milnor book, Morse series. So V is easy to construct. And now I should recall.
Sorry, why from this fact follow one?
Because I make a picture. In topology, you want to make pictures. Suppose that this is V, this is D, and then you have X. You just take this. So this is X. And let's say that this is D, which can be said to be a face of your. And now you take just inside your triangulation, you just increase a little bit the border to obtain something which is open. And okay, I mean, it's just a sketchy proof, but I think that you can imagine that if you have a sub-CW complex, you can always take an open set which is homotopically equivalent to it.
That's why you assume
Huh?
So that's the reason why you
No. The reason is coming now.
Excuse me, with this, maybe we need that instead of topically equivalent homomorphic. Otherwise, how we take from the CW complex homotopically equivalent to X, how we can take the preimage of this open? It also can be not open.
Now, what okay. Suppose that you have a point. I will change the point by a disk. So this is homotopically equivalent, but this is open and this is not open. So suppose you have a line. Instead of taking a line, I will take this. So you see, the line is a closed set, but this open set is homotopically equivalent to my line, which is closed, but is an open set inside.
This W complex, not X.
Yeah, but anyway, you can you can arrange things to obtain the things that is. Yeah, I think that I will not give the details of that because.
use triangulation, it's easier.
Huh?
We can use triangulation. The fact
Yeah,
that
this is what I am.
this is not the same. Okay. So you can triangulate the variety in such a way that this
Is
part of the triangulation.
exactly. Exactly. This is what I wanted to do. This is my picture. Yeah, you take a triangulation of the variety such that D is part of the triangulation, and then you enlarge a little bit. And this was, yeah, I'm sorry if I wasn't clear enough. So now we need a crash course, how you say, overview of Morse theory. And in order to do this, we leave for a moment the realm of complex geometry, and we work over for differential geometry. So let M be a C infinity variety and I suppose that I have a function f from M to R. A point P x0 in M is said be critical if df of x0 is equal to 0, which means that all the derivatives, so locally you can write f as a function in dimension of m varieties, and you suppose that all the derivatives vanish. And this okay. And if x0 is critical, you can define the Hessian of f in x0. And this is given in the following way. You take two vectors v1, v and w in the tangent space of M in x0. You extend, for instance, W to a vector field of around x0, and you define the Hessian of f in x0 on of vw to be v, to extend w to a vector field w tilde of w tilde of f calculated in x0. And I give the definition in this way, and now this is a bilinear form. It's a symmetric bilinear form on Tm. And it's symmetric because you have that v of w tilde of f minus w of v tilde of f is just that the Poisson bracket of vw of f in x0. And this is equal to 0 because x0 is degenerate. So you see that it's symmetric because this is equal to this, because the other is 0. And I like to do the definition like this because this shows you that it doesn't depend on coordinates. So you can change. And actually, if f is given by some in coordinate by f1, fn, with coordinate x1, no, sorry, by some function f of x1, xn, then the Hessian of f in x0 is the bilinear form associated to the matrix okay. So you see, and the point x0 is said to be non-degenerate if the Hessian f in x0 is a non-degenerate bilinear form.
And when you prove that it is bilinear, the form, maybe there you want to say x0 is critical, not general.
It's critical, yes. So this is well defined only if it is critical. So since it is a symmetric bilinear forms, all the eigenvalues of this matrix are real, and since it is non-degenerate, they are all of them are non-zero. Okay? So if x0 is a non-degenerate critical point for f, how you call it? There exists in T x0 of M a biggest subspace where the Hessian is defined, negatively defined. Space, let's call it N. Is negatively defined. And its dimension is called the index of f at x0. which is an integral number which is between 1 and the dimension of x. No, because it's non-degenerate. Huh?
All the eigenvalues can be positive.
Ah, yeah, 0, yes, sorry. Sorry, yeah, you're right. And yeah, I need another definition is if f from M to R is like before, I will and A is a real number, I will define to be NA to be f minus 1 of minus infinity A. So the theorem, the main theorem in Morse theory, is suppose that for every A, NA is compact. And let C a real number, and suppose that f minus 1 of C contains R point, R non-degenerated, contains only R points, no R critical points which are non-degenerated of index are only critical point x1, xr of index lambda 1, lambda r. And no other critical points. Let epsilon bigger than 0, and we suppose that MC plus epsilon do not contain critical points. So then MC plus epsilon plus. Yeah, but now
MC, so it's the difference between MC plus epsilon minus MC that does not have.
yeah, minus MC. Yes, sorry, thank you. do not contains any other critical point, then MC plus epsilon has the homotopy type of MC minus epsilon with a cell of dimension lambda I attached to each point xi. So and now I will try to make the famous pictures in Milnor book, but I am not very good. And I consider the height function, and here is this point is sent here, then here, and so on. Okay, let me make the picture good. So it happens that before this point, let's say alpha 1, the preimage is empty, so it's compact. Then at this point, I have a critical point, and I will add, and you will see that I'm at just a point, and then I am, if I take alpha 1 plus epsilon, I'm just adding a zero-dimensional cell, which is a disk, which is contractible, which is homotopically equivalent to a disk. When I arrive here, I will find another critical point. And I think that here, what I'm doing is I add this. And I'm adding a one-dimensional cell like this. This is homotopically equivalent to this. Because you can increase this thing. And when you arrive here, it becomes so here. So this is what happens in alpha 2. Then you have alpha 3. This is, let's say, after. So this is alpha 2. Then nothing happens till here, till alpha 3. The homotopy will not change till alpha 3. And in alpha 3, you're adding something like this, which is essentially equal to this. And then you arrive here, alpha 4. and you add another cell to close the. No, it's MC minus epsilon, and then you add yeah, MC, yeah. So this is a way to reconstruct a torus from this Morse function. This is called Morse function, which tells you that your torus is constructed by building up cells following the rule given by this function. Okay? And now we would like to study the situation in the case of complex varieties. And there is okay. You see that there are many conditions here, but what is nice is the following theorem, which says that if M inside R M is a differential variety, and P is a point in Rm, I can consider the map dp from M to R given to x0 send to the x0 minus p square. This I can always do it. And actually, for almost all P in Rm, dp will have only non-degenerated critical point. This is an application of Card theorem, essentially. So that tells us that at least for varieties which are inside the space, the Rn, it is very easy to find a function which verify this kind of condition. In particular, this theorem coupled with this theorem tells us that these varieties are triangulable. They are homotopy equivalent to CW complex because they are constructed by building up pieces. You see, they are constructed by building up cells. Adding cells, yeah.
I have a question about the Morse theorem. You said that you were touching the cell to the critical point.
Yeah.
But by the touching, we always touching along the boundary or not?
Yeah, this is what I said at the oh, I didn't explain.
In your picture, it's not along the boundary, but the critical point is getting by, let's say,
yeah, but the boundary of this is this. And now I am. Sorry?
Are the critical points on the boundary of the cell you
yeah, in some way, I should exactly. If you want, I should. I can. Yeah, it's not easy. You see now? You see that now I am attaching one. This critical point. And now I knew that I didn't have to make this picture. How can I explain this? I should do it. I'm not able to make the picture. And so I think that the best way to make the picture is this, but this is homotopically equivalent to attaching this cell. In some way, you see, you can restrict this, and then you attach it to just one point. Okay? So I'm sorry, it was just a way to indicate how to do it. But anyway, it works. Now we come, I think that I said everything I wanted to say about Morse theory. Yeah. And now we come to the proof of Andreotti and Frankel. The proof of Andreotti and Frankel is will pass. We have let's say 2 steps. One step is the following theorem. Now, okay, first of all, I will have x inside Pn, PR, dimension, complex dimension of x is equal to n, which is bigger or equal than 3. And I would suppose that D is x intersected with the hyperplane at infinity. And this is just, this is what, when I said very ample instead of ample, it is not really a restriction because a multiple of D will have this property. And, but the homotopy, the fundamental group of a multiple of schemes do not change the scheme. They do not change. So let's put ourselves under this hypothesis. So I have x0 inside the CR is an affine variety of dimension n, smooth. So if I identify CR with R 2r x0 becomes is a differentiable variety. Okay, so I am in the situation to apply techniques from Morse theory. And oh gosh, that's wonderful. So for almost, so I can apply this theorem, so I can always suppose that I am using function of kind t dp, and these functions are with only non-degenerate critical points for my x0. Okay, so I will suppose that. So I fix d0, p0, p in R to n such that dp from x0 to R is with only non-degenerated critical point. And now the theorem, the first theorem one proves is that let x0 be a critical point for dp under this the hypothesis we have here, then the index of x0 for dp is at most n. So you see, the interest of this statement is, which actually would give, but I will not describe it here, a proof of Lefschetz hyperplane section theorem for cohomology with integrals coefficient, which tells us that x0 is a priori a variety of dimension 2n, a real variety of dimension 2n. But from the point of view of homotopy theory, actually, it just is obtained, is just counting for the half of the dimension. It's just counting, for the point of view of homotopy theory, it is just obtained by cells of dimension 1/2 of it, which is typical of complex varieties. And this has this okay, this is the key point.
Also, here is needed n greater or equal to 3.
Eh?
For this theorem is needed greater n greater or equal to 3.
No. No. This theorem is always true. But you see, if you take a surface, this will mean that in order to have some influence on the fundamental group, you have to control cells of dimension 0, 1, and 2 because of the exact sequence of homotopy. So as soon as you are bigger, you don't have, but 2 may create problem for the injectivity. Okay. Okay, I will leave the proof of this for a moment, and I would like to see how to deduce Lefschetz theorem from this. You have to modify a little bit this dp. So I will change this function. I will consider the function f from x to r, which is given by f of x is equal to 0 if x belongs to D, and 1 over dp of x if x is in x0. And if necessary, you can smooth it a little bit to obtain that is differentiable. And now, you see here there is the function is to the denominator. So it means that if you compute the index, the derivatives will, in order to compute the second derivative, you have to compute the composite of the derivative of d and the derivative of 1 over t. Okay, this is and this the derivative of 1 over t is negative. Is minus 1 over t squared. So I will not make the computation, but you can check by simply an explicit computation, which if I do it, I will make a mistake, so I will not do it, is that if x0 in x0 is a critical point of dp of index lambda, then x0 is a critical point of dp of f of index 2n minus lambda. Simply change, because this is due to the fact that if you compute the eigenvalues of the Hessian of dp, and you compute the eigenvalues of the Hessian of 1 over dp, you simply obtain a change of sign. This is due to the fact that the derivative of this is negative. Okay? Which is bigger or equal than n. this is because of theorem 1.
It's not really F, you say, some modification, because this is not smooth, I'm wrong.
Well,
Because the second part cannot be zero, so you cannot, it is not smooth.
yeah, what I will do is the following. Sorry, okay. Okay. You can do two things. Either don't care about this problem, which is the correct attitude, but otherwise you just suppose that x0 is not in this v which we changed, defined at the beginning. We suppose if x0 is not in v, where v was defined at the beginning of this proof, or even something a little bit smaller than v, okay? And then you smooth v f inside v. So you don't care what happens inside v. Inside there's something a little bit smaller than v, okay? So now you take x epsilon to be some f minus 1 of minus infinity epsilon, so small that it is contained in V. Okay? You can do it because this is at least is continuous. Okay? So you choose epsilon so that this property is verified. Okay? And now you can apply Morse theorem. Will tell you that x is obtained from x epsilon adding cells of dimension at least n, which is exactly what we wanted. Okay?
Since you put 0 on OD and the function is positive outside of D, D should be a set of critical points.
Yeah, but look to the statement. I care about things which are, I don't, you see, you can do by hands. The variety C plus epsilon is obtained from the variety, the smaller variety, adding cells. So I have D, then I have, this is D, then inside I have this V, and then I have this weird x epsilon. I don't care what happens before. at the point for the point of critical point. I just want to be sure that except to build up all the x, I just need to consider x epsilon and adding cells of bigger dimension. So what happens here, I don't know. Okay? And now, so this is the proof of the fact that if I prove theorem 1, I finish the proof of Lefschetz theorem. Because theorem 1 made me build this function, and the critical point of this function are of index bigger than n, and then I can apply this argument to obtain a function which has, so I builded x epsilon, and x is obtained from x epsilon at its cell of bigger dimension.
Where is the smoothness of D used?
Not used, actually. Not used, actually. There are statements where you can even say that you can improve the statement saying that the singularities of x must be contained in D and so on.
No, I mean, if I take a singular divisor in a variety dimension at least 3.
Yeah, you need that the variety is smooth outside the divisor. Yes, but I didn't want to enter to this kind of. So I need to prove this statement. This statement, at some point, you have to make some calculation, because until now they were mostly speculations. So let me see. No. So, proof of theorem 1. So, the point is the following. So, I can make, so as you remember, in order to define a critical point and the Hessian, so also this so also the definition of the quadratic form, I was quasi intrinsic. Okay, I was intrinsic, and then I gave you a formula to write them by using derivatives. But so it requires a little bit of small observation, but I can suppose that the point x0 is the point 0, 0. And the point P, so x is of dimension n. P is the point 0, 0, 1 at the position n, 0. And 0 is given as the graph of a function f from, well, let's say, an open set of Cn to Cr minus n. This is because the variety is smooth, and then you can always suppose that this is this. You can always make change of variable, analytic change of variable to obtain this. So x0, it is given in a neighborhood of x0, is given by z1 zr, f1 of, let's write in z, fn minus r of z. Yeah. Now, let's say that you have a CR inside Cn, which are given by z1 zr to what I said before, z1 zr, f1 of z, fn minus r of z. So this is, let's say, x0. And dp of z1 zr is given by sum from I to 1 to r zi square plus fr of z minus 1 square plus sum from I from j from r plus 1 to n of fj z square.
Is the position bigger than n, the 1? Because here that's non-degenerate.
N plus r plus 1, yeah. Yeah, sorry, you're right. This is at the position r plus 1. One more. One more. The dimension of n. Yeah. N. I changed the. Yes, I'm sorry. I changed the n. R minus n. F1 lies j from 2 to r minus n. I think that now is correct. Okay? This you make as more, and the fact that x0 is critical means that you can compute explicitly, the order of vanishing of Fi at 0 is at least 2. You just make an explicit computation, and you will see what happens. Up. And this can be written also as the sum of zi square plus 1 minus 2 times real part of Fr plus F1 of Z plus sum from j to 1 to n minus L or Fj Z square. Remark here is 2, and now is 1. Okay? It's just to write down what is this explicitly. Okay? And now you can write F1 of Z as a quadratic part plus another function, F1 tilde of Z, which this is a homogeneous polynomial two, and this is a function vanishing at order at least 3 on 0 in 0. I just write the Taylor expansion of the function. And now you make again an explicit computation, and you check that this part doesn't play any role when we compute the Hessian. You can forget this part. It's just compute the derivatives and you will see it. And so you obtain that the Hessian of the Hessian of dp on x0 of x0 at the end it will be 2 times minus 2 times the Hessian of the real part of Q2 in x0. No, the minus is here, and here is plus identity. I have to mention that. Here I'm writing the matrix associated with that. You just compute the derivatives of the second derivatives of this with respect to z and z bar, because they are 2 variables, and this count for this part, and these do not count, this count for this part. What I mean is that when you want to compute the double derivatives, and then you compute in 0, since this is of order bigger or equal than 3, the derivatives, the double derivatives, they all vanish in 0. So these do not count in derivatives, and the only part which counts is this. And then you have to check that you are taking only the real part of that, because here there is the real part. It's a computation you can do in one variable if you want, and it will work even in n variables. It's a and now you do explicit computation is now, so you have to compute this, and you have that this lemma, which says that let Q2 be a homogeneous quadratic polynomial of degree 2, then Q2 of x z1 zn, then the Hessian of the real part of Q2 as at most n positive eigenvalues. And this is very easy, because you can change in variables. This doesn't change anything. You can suppose that Q2 is of the form z1 to the power 2 plus zs to the power 2, where s is smaller or equal than n. So the quadratic form and then you write zi as xi plus I plus square root of minus 1 yi, and the quadratic form associated to Hessian of the real part of Q2 is x1 square minus 1 square plus xs square minus ys square. So you see that the number of positive eigenvalues are just s. And now you put the eigenvalues here, and you play a little bit with this matrix, and you obtain the general the theorem that number of what is it? The index at x0 must be at most n, because you have here is at most n, then you change the positive are at most n, so this change the sign, and the number of negative are at most n. This is just a computation you can do in linear algebra. So and this ends the proof of Andreotti and Frenkel theorem. Half an hour after I believe it, I could end it. But I would like just, I will come back to this tomorrow, but I would like to notice two things. in order to obtain this proof, of course, strongly uses topology, strongly uses differential geometry, strongly uses R. Even the ordering, the fact that R is completely, is well ordered. And so a priori there is no way to find a way to generalize this theorem to algebraic geometry, to a more general situation in algebraic geometry. But we would like to notice that in order to prove this, we had to introduce some neighborhood of the divisor at infinity, this V, and some understanding on function, their Taylor expansion. And in the proof used yesterday of Siegel theorem or Chow theorem, one key point, 1 minute, 30 seconds. One key point was to use the Taylor expansion again of global section in some points. So formal geometry would be a way to introduce a concept in algebraic geometry which play the roles of these tools: neighborhood of points, Taylor expansion of function, and neighborhood of subvarieties of variety. And by using this, you can prove an interesting theorem in algebraic geometry which are similar to this one. Thank you.